In this video, we're going to implement an autoencoder through coding. Specifically, among the many things an autoencoder can do, we'll focus on dimensionality reduction using the iris dataset, and then compare the results with PCA, one of the most well-known dimensionality reduction methods. The coding files are available on GitHub, so feel free to download them and try running the code yourself. PCA, or Principal Component Analysis, is a widely used unsupervised learning method for reducing the dimensionality of datasets. For example, if you want to reduce a dataset with 10 features down to 2 features, PCA performs a linear transformation to create new features, often called something like Z1 and Z2, and reduces the dimensions in this way. So, PCA is essentially a linear dimensionality reduction method based on mathematical calculations. First, let's implement code to perform dimensionality reduction using PCA. We start by importing libraries like NumPy and Pandas, as well as min-max scalar for normalization. To visualize the results, we import matplotlib, and for running PCA, we bring in the PCA module from scikit-learn. Next, we load the Excel dataset into a variable called df and convert it into an array for faster computation. In this Excel file, the 3 iris species, setosa, versicolor, and virginica, are represented by the numbers 0, 1, and 2, which we assign to our Y data. For the X data, we perform normalization using min-max scalar, and then assign it accordingly. What I'd like to point out here is that, although in building a model it's standard practice to split the data into training and test sets, the purpose of this code is to cluster the data in a lower dimensional space. For that reason, we didn't split the data into train and test sets, and instead use the entire dataset. Now, we'll use PCA to reduce the dimensionality of the data. For visualization purposes, we'll reduce it down to 2 principal components. We'll name these 2 components PC1 and PC2, and to use the species as a legend in our plots, we add a column called target, containing the actual species from the Y data. This way, we get a dataset that includes the 2 reduced principal component values along with their corresponding species, like this. Based on this, if we plot PC1 and PC2, we get a graph like this. To distinguish the 3 species, we use different colors and markers, blue, orange, and green, and label them as setosa, versicolor, and virginica, respectively. This way, all 150 iris data points are plotted on the 2 principal components, making it easy to see which species each point belongs to. In conclusion, PCA with 2 principal components shows that the species are well grouped and clearly separated. Now, let's implement code to perform dimensionality reduction using an autoencoder. As explained in the previous video, an autoencoder is a neural network-based, nonlinear method made up of an encoder, a latent space, and a decoder. When high-dimensional input data passes through the encoder, it's transformed into a lower-dimensional, latent space. Then, the decoder uses the information in this latent space to reconstruct the data back to its original dimensions. During training, the model minimizes the difference between the input and output, effectively compressing the important features, which is how dimensionality reduction is achieved. Just like we did with PCA, we'll now implement dimensionality reduction to 2 dimensions, using an autoencoder on the same dataset. First, we import the libraries needed for autoencoder coding, such as TensorFlow and Keras. Loading and preprocessing the data is done in the same way as in the PCA example. The shape of X data is 150 by 4, where 150 is the number of samples and 4 represents the number of features in the dataset. We set the dimension of the latent space to 2, so the autoencoder reduces the data to 2 dimensions. The encoder is made up of 3 layers. It takes the original 4-dimensional input and outputs a 2-dimensional latent vector at the last layer. The decoder also has 3 layers. It takes the 2-dimensional latent vector and reconstructs it back to the original dimension. Here, the linear activation function means output the input as is. It is commonly used in autoencoders because we want to reconstruct the original data as accurately as possible. Next, we connect the encoder and decoder to build the autoencoder. The input data passes through the encoder and then into the decoder, defining a model that flows from input to output. We then compile the model using the atom optimizer, which is well suited for stable training, and we use the mean squared error as the loss function. After that, we train the autoencoder on X data for 50 epochs. Since the input and output of an autoencoder must be the same, both are set to X data. This allows the model to learn to reconstruct the input from the latent space. During training, the loss values are stored in the history variable. If we plot them, we can see the loss steadily decreasing over time. Next, we use the trained encoder to reduce X data into 2-dimensional latent vectors. We name these 2 latent vectors Z1 and Z2 and add a column called target containing the actual species from Y data. This gives us a dataset that includes the 2 reduced latent vector values along with their corresponding species, like this. Based on this, if we plot Z1 and Z2, we get a graph like this. To distinguish the 3 species, we use different colors and markers, blue, orange, and green, and label them as setosa, versicolor, and virginica, respectively. This way, all 150 iris data points are plotted on the 2 latent vectors, making it easy to see which species each point belongs to. In conclusion, dimensionality reduction using an autoencoder with 2 latent vectors shows that the 3 species are relatively well grouped. Additionally, the blue setosa points form a separate cluster, while the green and orange points are located close to each other, showing the same pattern we observed in the earlier PCA analysis.